Hey Precalculus, in this video we're going to be doing section 4.5, which is graphing tangent. So tangent on the unit circle, which I have as a visual for you, right? Tangent has a period or a cycle between 0 degrees or 0 pi and pi, or 0 and 180, right? So this is one cycle. I know that because from here to here, or at this point, it's when our tangent values start to repeat, right? So tan of 30 is root 3 over 3, and tangent of 210 is also root 3 over 3, right? So the period is shorter than sine or cosine, secant or cosecant. So when we're graphing tangent, that'll be slightly different. The other thing is it's undefined, right? So tangent is undefined at 90 degrees and 270. So that means that if it's undefined, it's going to have asymptotes. So first of all, let's talk about the generalized equation. So the generalized equation is very similar to all the others. It's going to be y equals a times tangent of bx plus c plus d. Now your period is going to be found using, I guess it should be equal signs since it's an equation. Your period is going to be whatever a normal period is divided by b, just like for sine and cosine and stuff. But that's a distance of pi because it's tangent. Right? So a period is pi divided by b. Your period, the way it looks, is it's your distance between the asymptotes. Okay. A is can be like a vertical dilation. So it's your vertical distance between your midline, which I'm going to put in quotes because we don't actually graph it typically, and your critical points. Bx plus c equaling 0 will give us our phase shift. And it's actually going to be between your asymptotes. It'll be the middle of your asymptotes. Okay, and the last thing is D, right? So D is a vertical shift or your midline. Or your sinusoidal axis. Okay, so to graph, what you're going to do Okay, so when you're graphing, the first thing you want to do is determine like all your stuff, like your period, your midline, if you want phase shift, The second thing you want to do is find the equation of your asymptotes. To do that, you're going to do bx plus c. But instead of equaling 0, you're going to set it equal to b pi over 2, because that's where you're undefined. And then we're going to do, because we want negative values too, so we're going to go from negative pi over 2 to pi over 2. So you're going to do bx plus c equals pi over 2 and solve for x, and bx plus c equals negative pi over 2 and solve. The third thing you want to do is determine your critical point distance. And that's going to be your period divided by 4. And then graph. Be careful, so just like with sine, cosine stuff, everything we've done so far, your scale is important. Your scale is determined by looking at your asymptotes and your critical point distance. Alright, so let's do an example. And then call it good. So we're going to do y equals 3 times tangent of 2x plus pi over 2 minus 1. So like I said, first thing we want to do is find all of our stuff. So really the only thing you need is like your period and your midline. I realize you can't see what I was pointing to. So your period, right, is pi divided by b. So in this case, it's pi over 2. Our axis midline is y equals negative 1. Now, you could find your phase shift, but we really don't need to because your phase shift, remember, is always going to be in between. It's in the middle of your asymptotes. So we can go straight to just finding our asymptotes. And those are going to be vertical lines. So I'm going to take bx plus c, 2x plus pi over 2. And I'm going to set it equal to pi over 2 because that's where we're undefined. So when I subtract, I get 2x equals 0. So that means x equals 0 is one asymptote. And there's more than one asymptote or two asymptotes, guys. But this is just going to give us our baseline for like where we're starting. Alright, so 2x, negative pi over 2 minus pi over 2 would be negative 2 pi over 2, which is just negative 1. So then that means x is going to equal negative pi over 2. And the critical point distance is going to be a period divided by 4. So that's times 1/4, which equals pi over 8. Right, so when I'm setting up my coordinate plane, which you guys will be given one on Alex, which is really nice, I want to look at my critical point, right? Critical point distance is pi over 8, and my asymptotes are at 0 and pi over 2, so common denominator will be pi over 8. So my sinusoidal axis is at 1. My amplitude, if you will, is 3, or negative 1. So I'm going to go up to 3 and down to negative 5 for my y-axis. and then 1/8. Right, so that'll be pi. So 1, 2, 3. This will be pi over 2. 8, 4 eighths negative pi over 2. All right. So if you want to do like a light sinusoidal axis, you can. But technically, we don't include it with our graphs typically. I think Alex actually lets you. So this is where our sinusoidal axis is. That's where we're going to count for these. Our asymptotes are going to be what you want to graph first. So our asymptotes are going to be x equals 0 for the parent, right? And then at negative pi over 2. Okay. Now, our first key point is our phase shift, which is, remember, halfway in between your parent asymptotes. So that's going to be at negative pi over 4, comma negative 1. Then you also could have done bx plus c equals 0, and you also would have gotten negative pi over 4. Okay, so now there's 2 more points that we need to plot here. So what you do is you're going to go to the right by your critical point distance. So we're going to go right pi over 8, and then we're going to go up according to our dilation or amplitude, if you want to call it that. So 1, 2, 3. So, and then critical point distance to the left, down 3. And because we have asymptotes, I always am rusty, it's been a while. Oh, that's terrible. Alright, that's not as bad. So this is going to keep repeating the pattern. So from here, right, the distance between our asymptotes is 1, 2, 3, 4. So I'm going to have 1, 2, 3 asymptote. 1, 2, 3 asymptote. Same to the left. So halfway in between. And then right the critical point distance and up 3. Left critical point distance down 3. So it's kind of like a little bit of a turning point. Like a cubic function almost. Cool. And that's it. So plot like the first period of it, and then you can just model that for all the other periods.